We are 12 days away from an answer that could rewrite the rules. On October 29th, a fast-moving object cataloged by the Atlas survey will swing past the sun at just 30 million kilometers. And in those few critical hours, telescopes across the planet and spacecraft near our star will finally reveal whether what we're tracking is an ordinary long-period comet or the third confirmed visitor from interstellar space. The clock is ticking, the data windows are narrow, and the stakes have never been higher. Right now, somewhere between the orbits of Venus and Mercury, an object provisionally called the Atlas Interstellar Candidate is racing sunward on a trajectory so steep and so fast that weeks of analysis still haven't ruled out an origin beyond the solar system. If the final orbit solution holds, we're looking at an eccentricity above 1.0, meaning this thing didn't begin its journey in the sun's gravitational sphere. If it drops back below that threshold after accounting for outgassing forces, we've got a comet on an extremely elongated but still bound path. Either way, October 29th is the moment of truth, because perihelion passage offers the brightest, closest, most data-rich window we will ever get. Today, you're going to learn what's confirmed about this object, what changed in the last 48 hours, why multiple independent teams are watching the same patch of sky, and what the geometry of the approach means for observers in both hemispheres. You'll hear which anomalies are raising eyebrows, which have straightforward explanations, and which sit in that uncomfortable zone where speculation begins. Everything you're about to hear comes from public databases maintained by the Minor Planet Center, JPL's small body database, the SOHO and Stereo Solar Observatories, and reports filed by professional and amateur astronomers coordinating through the Central Bureau for Astronomical Telegrams. No leaks, no inside sources, just the data trail left by an object that refuses to fit neatly into any box. Here's what's rock solid. The Atlas survey on Mauna Loa picked up a faint, fast-moving point of light in the first half of October 2025. Initial astrometry showed a hyperbolic incoming trajectory with an eccentricity around 1.1. That number is preliminary, and it comes with error bars, but it immediately flagged the object for follow-up. Within 72 hours, observatories in Chile, South Africa, and Australia contributed additional positions. JPL's orbit solution, updated 3 times in the past week, still lists an eccentricity greater than 1, though the uncertainty range now dips just below that threshold depending on how you model non-gravitational forces. Perihelion is currently computed for October 29th, plus or minus 6 hours, at a distance of 0.2 astronomical units. That's inside the orbit of Mercury, deep in the sun's glare, and it means ground-based observation windows are closing fast. Brightness is where things get interesting. When first detected, the object sat around magnitude 16, faint enough to require a decent telescope, but well within reach of survey instruments. Over the last 9 days, it's brightened to somewhere between magnitude 11 and magnitude 9, depending on which observer you trust and what filter they used. That's a jump of 5 to 7 magnitudes in less than 2 weeks. Comets do this all the time as they approach the sun, but the rate here is steep. A classic comet brightening curve follows a predictable power law tied to distance and activity. This one matches that curve in some reports and overshoots it in others. We don't yet have a published light curve with error bars from a single controlled source. So right now we're stitching together snapshots from multiple teams using different equipment. What changed in the last 48 hours is the appearance of a faint tail in images taken by observers in the southern hemisphere. It's short, maybe half a degree on the sky, and it's oriented roughly anti-solar, exactly where you'd expect dust pushed by sunlight in the solar wind. That tail is evidence of outgassing, which means surface ice turning to vapor, which strongly suggests a comet. But here's the wrinkle. The tail showed up suddenly. One night, nothing. 2 nights later, a clear feature. Comets can have outbursts, sudden releases of bump and dust when a fresh patch of ice gets exposed or a subsurface void collapses. Outbursts are common and well documented. They're also one of the main reasons orbital eccentricity calculations wobble, because every puff of gas acts like a tiny rocket thrust, nudging the path in ways pure gravity doesn't predict. Spectroscopy is the gold standard for understanding what something is made of, and we have exactly one preliminary spectrum so far. A team using an 8-meter class telescope in Chile grabbed a low-resolution visible light spectrum on October 15th. The data show a blue continuum, meaning reflected sunlight off dust, and possible emission features near 388 nanometers, which would be consistent with CN, a molecule you see in Comet Comey all the time. The signal to noise is marginal, and the team hasn't published a formal analysis yet, but the presence of CN would be another strong tick in the comet column. Interstellar objects can outgas too. We saw that with Oumuamua's non-gravitational acceleration and Borisov's obvious coma, so a tail and a spectrum don't by themselves rule out an extrasolar origin. They just tell you there's ice and it's sublimating. Now let's talk geometry, because where this thing is coming from and where it's going matter just as much as what it's made of. The orbit, if hyperbolic, brings the object in from a direction roughly 30 degrees above the ecliptic plane, the flat disk where most planets and comets live. The inclination is high but not extreme. If you trace the trajectory backward and subtract the sun's motion through the galaxy, the incoming radiant, the point on the sky the object seems to be coming from sits in the constellation Lyra. That's nowhere near the solar apex, the direction the sun is moving, so this isn't something we're running into. It's not aligned with any obvious nearby star either. The outbound path, assuming perihelion doesn't break it apart, would send it back out into the southern celestial hemisphere at a steep angle, invisible to northern observers by mid-November. Why does October 29th matter so much? Perihelion is the moment of maximum heating, maximum outgassing, and maximum brightness. It's when every instrument we have, from ground-based spectrographs to spacecraft coronagraphs, gets the best possible look. Close to the sun, solar flux is intense. Surface ices turn to gas rapidly, and any volatile materials hidden beneath a crust have their best chance to break through. If this object is a dormant interstellar iceberg, perihelion might wake it up. If it's a fragile comet that has never felt this kind of heat, perihelion might tear it apart. If it's something else, something with unusual composition or structure, perihelion will stress it in ways we can measure. The data we collect in a 6-hour window around closest approach will tell us more than weeks of tracking before or after. There's a second reason that data is critical. Right now, the object is moving into the sun's glare as seen from Earth. By October 27th, it will be less than 20 degrees from the sun in the sky, unobservable from the ground during darkness. By the 29th, it's effectively behind the sun from our perspective. We go blind, but we're not entirely blind because NASA's SOHO spacecraft and the Stereo Epto-A probe both carry coronagraphs, instruments that block the sun's disk and image the faint corona around it. Comets passing close to the sun show up beautifully in coronagraph data. If the Atlas candidate follows the predicted path, it should enter the SOHO-LASCO C3 field of view on October 28th and cross through C2, the narrower inner field, on the 29th. Stereo A will have a side view. Those images will be public within hours, posted to the SOHO and Stereo websites where anyone can download them. If the object survives, we'll see it emerge on the other side. If it disintegrates, we'll see a debris stream. If it does something unexpected, the world will know almost immediately. Physicist Michio Kaku, speaking on a recent broadcast, highlighted the significance of objects with possible interstellar origins and noted that perihelion passages offer rare natural experiments we can't replicate in any lab. He's right. We've had exactly 2 confirmed interstellar objects. One Oumuamua in 2017 and 2 Borisov in 2019. Oumuamua was rocky or metallic, showed weird acceleration, and left us with more questions than answers. Borisov looked like a normal comet, reassuring in its familiarity. A third confirmed interstellar visitor would give us the beginning of a population study. Are most of them icy? Are they fragments of planetary systems? Do they carry organic molecules? Every answer spawns 10 new questions, and every question pushes the boundary of what we understand about how solar systems form, evolve, and exchange material across light years. Let's raise the stakes a little more. We're deep into solar maximum, the active phase of the sun's 11-year cycle. The solar wind is gusty, Coronal mass ejections are frequent, and the magnetic environment near the sun is chaotic. A comet diving into that maelstrom doesn't just get heated, it gets sandblasted by particles, twisted by magnetic fields, and potentially ripped apart by tidal forces if it's loosely bound. Solar maximum also means space weather is unpredictable. If the Atlas candidate releases a big cloud of gas and dust right as a coronal mass ejection blasts through, we could see interactions we've never documented before. Ground-based observers coordinating with spacecraft data might catch plasma effects, ionization fronts, or even meteor showers if debris reaches Earth's orbit months later. None of that is guaranteed, but the timing is remarkable. Now the anomalies file. 4 things don't quite fit the standard comet template, and each one has a mundane explanation and a speculative angle. First, the brightness surge. Evidence, 5 to 7 magnitudes in 9 days, confirmed by multiple observers. Natural explanation, the object is small, maybe a few hundred meters, and a large fraction of its surface suddenly became active as it crossed some temperature threshold. Comets do this, what some speculate. If the brightening continues at this rate, it implies either a much larger active area than the size estimate suggests, or an unusually high albedo, reflectivity, possibly from surface materials we don't normally see. Second, the lack of a visible coma in early images. Evidence, the first 3 nights of observations showed a stellar point source with no fuzz, no extended halo of gas and dust. Natural explanation, it was still far enough out and cold enough that outgassing was minimal, or the coma was too faint to detect against the background. What some speculate, an object with very little ice, perhaps a rocky or metallic body, would stay inactive longer, and the sudden appearance of a tail could mean a surface layer finally eroded away. Third, the orbital uncertainty. Evidence, JPL has issued 4 orbit solutions in 8 days, and the eccentricity error bars still straddle 1.0. Natural explanation. Outgassing forces are hard to model without knowing the rotation state, the active areas, and the composition, and the object is faint, so astrometric errors are larger. What some speculate, if non-gravitational accelerations are unusually strong or directionally weird, we might be seeing asymmetric outgassing or even a tumbling, fractured body venting from multiple jets. Fourth, the timing coincidence. Evidence, C 2025 R2 Swan reached perihelion 3 weeks ago. C 2025 K1 Atlas is inbound in mid-November, and 240 P makes a close pass in early December. That's 4 interesting objects in a 10-week window. Natural explanation, we're looking harder than ever. Surveys are better, and small number statistics make clusters look more meaningful than they are. What we don't know yet, whether any of these objects share orbital elements that might suggest a common origin, like fragments from a larger parent body that broke up centuries ago. If you want to see this object yourself, here's the reality. From the southern hemisphere, you have until October 26th, maybe the morning of the 27th, if you have dark skies and a good horizon. Look east-southeast about 45 minutes before sunrise. The Atlas candidate will be roughly 15 degrees above the horizon, moving through the constellation Virgo. It should be somewhere between magnitude 9 and magnitude 7, which means binoculars will show it easily as a fuzzy star, possibly with a short tail extending upward and to the left. A small telescope, anything above 4 inches, will show more detail. Take a photo if you can. A 30-second exposure at ISO 1600 will pick it up. Northern Hemisphere observers, you are mostly out of luck. The geometry keeps it low and lost in twilight. After perihelion, if the object survives, it will emerge into the evening sky in early November, visible low in the west-southwest after sunset. Brightness predictions are unreliable because we don't know how much material will boil off or whether the nucleus will fragment. Estimates range from magnitude 6, naked eye visibility under dark skies, to magnitude 10, binocular only. The best nights will be November 2nd through 7th. After that, it fades and climbs higher into the southern sky. A telescope target only. Space-based observation is your other option, and it's the one that doesn't depend on weather or horizons. Starting October 27th, Check the SOHO LASCO images on the NASA website. The C3 camera updates every few hours. Look for a bright dot moving against the star field. Comets in LASCO images often look like tiny smudges with tails pointing away from the center. Stereo A data will be available on the Stereo Science Center site. If you've never watched a comet cross a coronagraph live, this is your chance. The images are raw, unprocessed, and they drop online within 2 to 6 hours of being taken. You'll be seeing the same photons the science team see at almost the same moment. Here's your reality check. What's confirmed? An object discovered by Atlas, currently brightening, on a trajectory that brings it very close to the Sun on October 29th, with a preliminary orbit that might be hyperbolic. What's likely, it's a comet, probably a long-period comet on an extremely stretched ellipse, behaving mostly as expected, but with an outburst or two that made the brightness curve steeper than average. What would count as a breakthrough? A final orbit solution with eccentricity definitively above 1.0 after accounting for all forces, combined with compositional data showing isotope ratios or molecular species inconsistent with solar system formation. That's the bar for interstellar confirmation. Anything less, and we've got a fascinating comet, but not a visitor from the stars. What would also be extraordinary, evidence of structure, not just a dirty snowball, but organized layers, unusual strength, or fragmentation that doesn't match collisional models. Oumuamua hinted at that with its weird shape inferred from light curve tumbling. If this object breaks apart at perihelion, the way it breaks and the size distribution of fragments will tell us whether it's a rubble pile, a solid chunk, or something in between. The next 72 hours are critical for ground observers. Every image, every spectrum, every astrometric position refines the orbit and builds the baseline against which perihelion changes will be measured. If you have access to a telescope, if you're part of an astronomy club, if you know someone without a good camera and a tracking mount, now is the time. Data submitted to the Minor Planet Center feeds directly into the orbit calculations the whole community relies on. You don't need a PhD to contribute. You need accurate timestamps, star field references, and careful measurement. This is citizen science at its most immediate. Professional teams are coordinating a perihelion campaign. Spectroscopy before and after, multi-wavelength photometry, polarimetry to probe dust grain, seizing composition, and radio observations searching for OH emission, the hydroxyl radical that traces water outgassing. The James Webb Space Telescope schedule is locked months in advance, so it won't slew to this target, but ground-based 8 and 10-meter telescopes are in the game. Expect preprints on the RRXA within days of perihelion and formal papers by December. What happens if it's confirmed interstellar? The object gets an official I for Interstellar designation, 3I/Atlas, and joins Oumuamua and Borisov in the record books. The trajectory gets traced backward through the galaxy, accounting for stellar encounters over millions of years, to estimate where it might have originated. Compositional studies get compared to exoplanet atmosphere data and protoplanetary disk observations to look for connections. And every telescope capable of detecting faint, fast-moving objects gets tasked with searching for more. Because 3 detections in 8 years suggests we're just starting to see the tip of a vast population drifting between the stars. What happens if it's not? We've still got a spectacular comet on one of the most extreme orbits ever recorded. A natural laboratory for studying how ice behaves under intense heating, and a reminder that the solar system's reservoir of long-period comets is vast and poorly mapped. Every close approach teaches us something. Every orbit refines, sharpens the models. Every spectrum adds a data point to the composition distribution. Science doesn't need aliens or catastrophes to be compelling. It just needs real mysteries and the tools to solve them. One more thing worth mentioning. The countdown framing isn't hype. 12 days is real. Perihelion happens whether we're ready or not. After October 29th, the object is outbound, fading, and geometrically harder to observe. We get one chance to catch it at peak brightness and minimum distance. One chance to grab the high-resolution spectra, the thermal infrared that probes nucleus temperature. the polarimetry that reveals dust composition. Miss that window and we're left with before and after comparisons and a lot of wishful thinking about what we could have measured. The universe sets the schedule, and we either rise to meet it or we watch the opportunity slip away. So here's what to watch. First, Soho Lascaux images from October 27th onward. If the object appears on schedule, we know the orbit is good. If it doesn't, something changed, and the scramble begins to figure out what. Second, post-perihelion recovery observations in early November. The first confirmed sighting after closest approach tells us it survived. The brightness and tail morphology tell us how it survived. Third, updated orbit solutions from JPL and the Minor Planet Center. Watch that eccentricity number and watch the error bars shrink. Fourth, any published spectra or compositional analysis. That's where the chemistry lives, and chemistry is destiny. If you're watching this on October 17th or 18th, you've got time to prepare. Check the Soho website bookmarks, find a dark sky spot for the 26th, charge your camera batteries, and set an early alarm. If you're watching this on the 25th or later, the window is almost closed, but Soho will still deliver. Either way, we're all on the same clock now, waiting for the same data, hoping for clarity and braced for surprise. The universe has sent us a puzzle with a deadline, and the answer arrives in 12 days. If you want to see how this unfolds in real time, hit subscribe, because the moment those coronagraph images drop or the first post-perihelion report hits the Central Bureau, you'll hear it here with the data, the context, and none of the nonsense.